Uh, Hello, I welcome everyone to this presentation. My name is Oliver Ozioko, and my affiliation is University of Derby in England. And the work which I'm going to present was carried out when I was still part of the Bendable Electronics and Sensing Technologies group at the University of Glasgow. So, which is led by Professor Ravinder Dahiya. So I'm going to go straight to my presentation, which is titled Spray-Coated Piezoresistive Bend Sensor for Controlled Movement in Soft Robots. Okay, just permit me to. Okay, so this is a brief outline of what we are going to be hearing in the presentation. So the first, I'm going to talk about the motivation, which is what led to the work itself, and then the fabrication steps for this very device. And also I'm going to be talking about the device characterization, and then some of the results we obtained, and then conclusion and acknowledgements. And of course, there will be a question at the end of the presentation. Okay, so this is the motivation. This summarizes the motivation for the work which I am currently presenting. So, and the motivation is for the fact that we were considering realizing a flexible crawling robot. So a flexible crawling robot which is made using thin substrates. And for us to be able to achieve that, we thought it would be a good idea to have also a flexible bend sensor, which will be able to control the serve as a closed loop control of the robot. And for us to achieve that, we have looked at the literature as well, and a number of strain sensors have been reported. And for piezoresistive strain sensors, we have realized that for some of them, they have the challenge of being unable to kind of distinguish between the like pressure. When you apply pressure, the resistance of the sensor changes. When you stretch it, if it is stretchable, the resistance of the sensor also changes. And when you also bend the sensor, the resistance also changes. So, and in this case, for the fact that we are not interested in the stretchability, we thought about avoiding those cases where stretching it will cause change in the resistance, and also when you apply force. So we now decided to go for a flexible sensor. Just flexible is flexible, bendable, but it's not stretchable. And this we need for our segmented flexible robots, which is also not stretchable. And for that, we are focusing mainly on the change in resistance that comes from the bending of the sensor itself. And for the actuation, we are trying to leverage on the device which we have fabricated before, which is called Sensact. And this device has integrated sensor and actuator, which in that case is a soft sensor that we used in that case. When you apply force, the resistance changes, and that resistance is used to control the actuation of the device. So we thought about using the same kind of flexible coil, which we have used for this, for the actuation of this flexible robot. So for us to achieve that, we thought also about having a flexible magnet as well. So, and we face some challenges for the flexible magnet, which is not part of this work because it's not able to generate the amount of force that we want. So we thought it would be good for us to reduce the weight of the device itself, which will help to improve the actuation and then enable it to actuate. So like I have in the figure here, there will be a magnet, a flexible magnet, and then a flexible coil, and also a flexible sensor. So the sensor will be used to measure the undulation happening at the different segments of this crawling robot. And when there's a bend, you'll be able also to know what's the bend angle, which can also be used for shape reconstruction. So at every point in time, we will be able to know, okay, this is the shape of this robot while it's in motion, and we know which part of the segment is being actuated, as the sensor information will be used as a feedback to control the magnetic actuation. Okay, so this is the main motivation for this whole work. And to realize this, we use the flexible substrate, which is the PVC. So, and we try to fabricate the sensor and the PVC to become part of the PVC so that there won't be delamination. And then when you apply force, there won't be apply pressure, there won't be sort of change in the resistance or significant change in resistance because it's not soft. So we thought about using this recoating approach so that when this is a part of the substrate and it's also flexible, there will be change in resistance when bending is applied, but not the other conditions. So we use the PVDF, which had very good adhesion with the PVC. So use PVDF powder, which was dissolved in DMF solution to realize a PVDF solution. And then in that PVDF solution, we added graphite powder. And this graphite powder, we now stirred that to realize a solution which has a DMF, PVDF, and graphite itself, which is the active sensing material for that. And by spray coating this on the PVC and curing it, we were able to realize a film which we can cut to any shape. And that film we can now use as the sensor. So depending on the size of where we want to attach this sensor, include the sensor, we can cut it to the shape that we want. And because of the good adhesion between the solution and the PVC, we realized that cutting it was not causing a lot of causing issue with the sensing itself, as we were able to cut it appropriately. Okay, so the other thing that we also did here was to attach the connectors for reading out the sensor output. And that is also a part where there's also a challenge, because if this is not properly done, there will also be there will also be change in resistance coming from the contact resistance. Okay, so and in that case, for us to overcome that problem, we use the conducting epoxy, and we also use low stress epoxy. I forgot the manufacturer at the moment, but we use this in order for us to realize a contact which is relatively less prone to delamination, which will help to overcome the issue with the change in resistance coming from the contact points. Okay, so we use this to attach on the film, and with that, our sensor was ready for characterization. And during characterization, because of the nature of the setup, we have used attaching the sensor to the setup. We need to put the sensor on another PVC, which is way bigger than the one we want to characterize, in order to have some extension for attachment to the setup. So we attach that to the setup, and we attach the sensor to that PVC, which increased the overall thickness of the material, and then we were able to now connect it to the setup. And the output of this was read using a LabVIEW program, which is a controlled via the computer. And also this setup is also controlled using a linear motor, which has about 0.1 millimeter resolution. And we're able to bend it to different angles in order to measure the change in resistance coming from this material. So this first figure here shows the sensor before bending, like I mentioned. And then in this case, we can see the sensor after or during bending. And the results which we realized can be seen here. So we carried out different characterization, which the first one shows the loading and unloading of the sensor. So we loaded the sensor in steps of 2.5 degrees bending, and then up to 35 degrees. And then we also unloaded to see whether it's able to return at least to the base. And although there are some drifts, but relatively it returned to the base. And also we carried out bending for up to 50 degrees in order for us to see what the sensor can do. And at 50 degrees, we saw that we had almost the kind of bend that we need for the application. What we also did was to test the sensor for stability. And for us to do that, we subjected it to a number of cycles, where we did up to close to 3,000 cycles, more than 1,500, as we can see here, but it was close to 3,000 cycles. And we saw the sensor was also responding very, very well. We also tried to subject the sensor for much longer, which we saw that the problem, the contact point also started to have some issue up to 5,000 cycles. We noted that the resistance was drifting more because of some delamination coming from the contact. That is why I mentioned in the beginning that the contact is also very key. And without the kind of epoxy we used, I think we wouldn't even go this far. So that is also something that needs to be improved further by making sure that the contacts are relatively firm and not delaminating during operation. Okay, so this concludes my presentation, and we were able to realize a flexible bend sensor using spray coating approach, and we use graphite as the main active element for the sensor. And this is intended for use for measuring the undulation of our proposed flexible segmented robots. And we hope in the future we'll be able to integrate this on a flexible robot, and then use the sensor output for closed loop control of the actuation coming from the device. I acknowledge those who have supported the work, and I thank you very much for listening to me.